Hello everyone, and welcome to a special episode of the Dynamics podcast series. I am Bong Lu Wei, and today I will be discussing a quick circular motion experiment that you can do at home. All you need is your phone, a gaming chair, and optionally some rope and planks. We will be examining how a radius of curvature and rotation speed of an object affects the acceleration experience, and by extension, hopefully derive the equations of acceleration that we have seen and applied in this course. We will place a phone a set distance from the center of the gaming chair. Optionally, at this point, you can also tie rope and a plank to the gaming chair to extend the possible arm moment, and spin it around at varying speeds for varying distances. The phone uses the Science Journal app's linear accelerometer, which is made to calculate the net acceleration of the phone. Thus, we should be able to see if the acceleration of the phone matches up with the predicted centripetal acceleration calculated by A equals omega squared times r, where omega is the angular velocity and r is the radius of curvature. In this particular version of the experiment, we made use of 3 different types of radius of curvature along with a 0 radius of curvature. We used 0, 3 centimeters, 9 centimeters, 18 centimeters, and 54 centimeters. In addition, we spun each of these at 36 and 72 RPM, which translated to 3.77 and 7.53 radians per second. From these, we could directly calculate the measured acceleration in meters per second squared. The results as follows were particularly perplexing. For almost the entire test, acceleration was only proportional to velocity and not radius. Acceleration did increase with radius at the very end, but not nearly to the calculated levels. Taking a look at this data, a couple of factors may explain this discrepancy in acceleration. Notably, the accelerometer for Science Journal, using the iPhone's accelerometer, is not always entirely accurate in its measurement of acceleration. For instance, the accelerometer just measuring acceleration in the z-axis, pointing through the iPhone screen, constantly stays at 9.8 meters per second squared, which represents the constant gravitational pull of the Earth, but in no way represents the actual net acceleration of the phone itself. Even if the phone is stationary, the accelerometer will still display 9.8 meters per second squared at all times. Furthermore, the accelerometer is also relatively imprecise, only displaying 1 decimal place. This could be either another software issue or a limitation on the phone's accelerometer precision, but either way, it means that any level of precision beyond 1 decimal place or 1/10 is not possible, and thus there could be a lot of inaccuracy involved with measuring acceleration with this device. Circular motion and centripetal acceleration are particularly important in aerospace when discussing how an aircraft turns. Generally, during a banked turn, as the aircraft tries to change angle faster or move at a higher velocity, the centripetal acceleration will increase. As a result, turning quicker or higher speeds puts more stress on the aircraft and pilot in the form of g-forces. Aircraft designers and operators need to make sure that both the pilot and the aircraft can withstand these stresses, which may also vary throughout the entire aircraft. At the same time, as a result of Newton's second law, which is force equals mass times acceleration, a heavier aircraft will necessarily have to undergo a greater amount of force in order to experience a similar amount of acceleration as a lighter aircraft. Thus, naturally, a C-5 Galaxy or some other type of super heavy cargo aircraft will have to be built much stronger than something like a Cessna. These differences in the forces experienced by each aircraft go a long way into informing how each aircraft is best designed and how they are used.